proton and the readdition of proton onto sorry, what am I doing? Oh, I'm adding proton first to make the OH, then I'm losing proton. You can do it either way. The exact sequence of these steps actually is rather nebulous. Just like, as I said, it's not quite clear whether proton is needed to activate the carbonyl or not. So we will, any mechanism goes. But here's the addition, okay? And at this stage, you can then envisage elimination of OH as protonated OH, namely water, facilitated by the fact that this electron pair can kick in to make an iminoimine, which is an octet structure. But notice this iminoimine has no proton, so it can't stabilize itself by proton loss from nitrogen to make the imine that we could make a couple of slides ago. Instead, it'll pick the proton next door and put in the double bond in this way. And one of the useful aspects of this that we'll see in chapter 18 is that this electron pair can donate into the double bond. You write another resonance form where this pair goes in here, and this electron pair goes out to make positive nitrogen and negative carbon, meaning that this carbon is electron rich. And it's so electron rich, sufficiently electron rich for haloalkanes to actually undergo SN2 reactions with this carbon, a very unusual situation. So that's why they're useful. So that's what happens with secondary amines. Here's a special application of amines where we're using hydrazine as the amine. So this could be called a primary amine, a special primary amine, where instead of an alkyl group, we have another amino function. This will undergo imine formation as advertised. Right? So you mix the two. This is done in ethanol. You don't even need any added acid or base. It will make the imine in this amino imine in high yield. These guys are called hydrozones, but we don't have to remember that. And it turns out that this is a useful reaction because it can be used in what's called the Wolff-Kishner reduction. When we treat these guys with a base, hydroxide base, at high temperatures, they eliminate nitrogen. And this is, in fact, why hydrazine is used here. Hydrazine is actually a rocket fuel. Hydrazine is several oxidation states away from N2. And N2 is rock stable. It's got a triple bond. And there's a strong driving force to make nitrogen. And hydrazine, for that reason, when mixed with oxidizing agents, is an explosive. Okay? So this is sort of used in this transformation here. Notice that with strong base, what happens is these two hydrogens, which one could call allylic hydrogens, move from the nitrogen here onto this carbon here. And N2, indicated in green as the leaving group, takes off. And what happens is they give you the hydrocarbon. So the Wolff-Kishner reduction, 2 steps, make the hydrazone with hydrazine and then treatment with hydroxide, is another way of getting rid of the carbonyl function. Turns the carbonyl into the CH2. So how does this go? First of all, high temperatures means 180 to 200 degrees. That's pretty rough. Chemists, in order to control temperature, typically like to use refluxing boiling conditions with a condenser up there because that means that the temperature is absolutely controlled. It's the boiling point of the solvent. Okay? So if you need a high temperature, you find a solvent, the boiling point of which is at the temperature that you desire. So that's why they use this particular beast here. It's an ether alcohol that boils at this particular temperature. So how does this go mechanistically? Here. Now, this is complicated enough, you don't have to remember that, but I want you to follow what is going on here, because it uses principles that we already know. If you stare at this long enough, you recognize that, and I already said the word, that these hydrogens are actually allylic hydrogens. Okay? It's a weird allyl system. You typically think of allyl as 3 carbons. Well, it's an allyl where 2 of the carbons are replaced by nitrogen. But it's still allyl. Anything next to any double bond is allylic, meaning that if you deprotonate, the anion is delocalized and stabilized by resonance. Here you get the extra kick that nitrogen is more electronegative than carbon. So this guy is actually relatively acidic. And so under the conditions of sodium hydroxide at relatively high temperatures, you get deprotonation to make the allylic anion. It's a diaza allyl anion. So this negative charge resonates with the carbon. It can be on nitrogen, it can be on carbon. Most of it will be on nitrogen because nitrogen is more electronegative than carbon, but there's a fair amount of negative charge on this carbon. And that allows the protonation of that carbon, that's the first proton shift, such that you get this intermediate with the weird name azo. This unit is called azo. And now the molecule actually smells blood. It realizes now it can be really nitrogen gas, and so it deprotonates once over to make this anion, and this anion kicks in the electron pair to make N2. Where is it? Here. And this carb anions, like alkyl lithiums, are extremely basic under the aqueous conditions. It's instantly protonated, and you get out the hydrocarbon species. Now, for vocabulary purposes, actually, the decarbonylation, the conversion of the carbonyl to, shouldn't call it decarbonylation, deoxygenation, turning the carbonyl into the hydrocarbon, can be done in one pot. All you need to do is take your starting carbonyl. I took a dione to show that if you have several carbonyls, they all get reduced. You boil it up with hydrazine and base, and here's the beast that I showed you earlier. It's called diethylene glycol, so it's like ethylene glycol extended, and that happens to boil at that high temperature. You don't need to remember that. All you need to know is hydrazine, sodium hydroxide, and delta. Okay? That's your vocabulary. And that will decarbonylate this guy and give you a good yield via hydrocarbon species. So this is now the third way we've learned to turn carbonyls into the corresponding hydrocarbon species. So that's a special application of imine formation. So we got oxygen nucleophiles, nitrogen nucleophiles. We keep on moving to the left. What about carbon nucleophiles? Well, you may say, oh, we already done that. Chapter 8. Grignards, alkyl lithiums, they add to carbonyls. Well, now I want to use very mild carbon nucleophiles, where this addition is reversible. And one such mild nucleophile is cyanide. In fact, cyanide was the first, that's chapter 6, nucleophile that we used in the SN2 reaction to make a new carbon-carbon bond. At the time, we didn't know what to do with it, but as we'll find out in this semester, cyanide is an extremely useful function for all kinds of other functional groups. So what do? We add HCN. HCN adds to the carbonyl to give these, there's a common name, cyanohydrins. They're really hydroxy nitrides. Again, proton adds to oxygen, cyanide adds to carbon. And this is reversible. So if you use excess cyanide, it goes from left to right. If you treat this with base to pull out the cyanide and solvate it, you go back to the carbonyl compound. So it's similar to hemiacetal or imine formation. In practical terms, we don't use HCN because HCN is a very toxic gas, used to be used at San Quentin and other prisons to execute murderers and related species. So the more practical use is sodium cyanide, which is equally toxic, but it's not volatile, okay? So much less dangerous. You can weigh it out, and then you add some acid to neutralize, to turn the cyanide into HCN and protonate the oxygen. And so mechanistically, the cyanide is a very good nucleophile. It's slim, small, so no steric hindrance. It gets right in there and attacks, kicks out the electron pair to the alkoxide, and then the proton that's floating around from either aqueous solution or a little bit of HCl protonates it, and you get the addition. And to reverse this, you add base deprotonates to make the alkoxide then eliminates cyanide. So you can go in either direction. And the usefulness is that you make a new carbon-carbon bond, and then you go to town with the functional group chemistry of nitriles that we'll discuss in chapter 20. So at the moment, we'll leave it dangling, but we'll come back to that addition because it's extremely useful to make hydroxycarboxylic acid derivatives. So here's a cute application in nature, the Bernard moth. The Bernard moth, the male, carries hydrogen cyanide in encapsulated form as a chemical warfare agent. Okay? And it's encapsulated as a cyanohydrin type adduct. It's attached to glucose. Glucose, we'll see that in the carbohydrates chapter, is the cyclic hemiacetal form of the hydroxyaldehyde. This carbon is an acetal carbon, and it's connected to this hydrogen cyanide adduct of acetone. That's exactly what this is. You see acetone, the two carbons. This used to be the carbonyl carbon, and HCN is added. The OH has been blocked has been used as an alcohol in an acetal. So this, when it uses this for chemical warfare, it hydrolyzes this acetal linkage. That makes the hydroxycyanide, and the hydroxycyanide then eliminates HCN, and you fire this off at your enemy. This compound is called linamarin. And the cute thing is that the male carries this and donates it to the female during the wedding night when they go off mating. Okay? So this is like a wedding night present. And the female is actually savvy enough to recognize in potential suitors which one carries the largest load of this stuff here, of the poison. Sort of like, the bank account. You go for the male with the largest bank account, because it then gets the poison, the weapon, and it profits obviously from the more the better, so to speak, and it can protect itself when it breeds and so forth. So here is hydrogen cyanide adducts in action. Here's another very useful carbon-carbon bond forming reaction that actually leads to double bonds. This is the so-called Wittig reaction, named after Georg Wittig, who, as a professor at the University of Heidelberg, got the Nobel Prize for this reaction in 1979, because it's really quite spectacular. He was interested, this is probably serendipity that they found this reaction, because he was interested in SN2 reactions of phosphines. People had published amines, they undergo SN2s, so he studied phosphines. Phosphines, as you may remember, below nitrogen, more polarizable, bigger orbitals, much faster nucleophiles, they're much more nucleophilic. So they react very nicely with haloalkanes, and they make phosphonium salts, just like amines make ammonium salts. So they made a whole bunch of these triphenyl phosphonium salts using triphenylphosphine, which happens to be a rather cheap phosphine. And they noticed that the positive charge on this phosphorus acidifies the protons on the carbon next door. So they started firing away bases at this, and they found that a very strong base will quantitatively deprotonate it. And the strong base to use is butyllithium. That's our strongest base that we have at our disposal. Right? Butyllithium pulls off this proton to make the anion. And you can write another resonance form for phosphorus. Third row, you can do valence shell expansion. The octet rule is no longer rigorous. If you don't like that, you can just stick with the octet rule, because that's the octet structure, and it's indeed the dominant contributor. And what you see is that this is now a potentially nucleophilic carbon, because it's anionic after deprotonating here. And so possibly by serendipity, I suspect somebody in Wittig's group tried to dissolve this stuff in a common solvent, meaning acetone. That's nicely polar, because this is a very polar structure. And then the reaction happened, instant reaction. And that reaction leads to a CC double bond. So what happened? This carbon, nucleophilic, attacks the carbonyl. Okay? And when it does that, you get this dipolar structure, a so-called phosphorus betaine. Plus attracts minus, it makes a four-membered ring, and then this four-membered ring, because of ring strain, and because when you cleave the ring this way, you get a PO double bond, which is also an extremely strong entity. There's a strong driving force for this. It generates a CC double bond. So this is a synthesis of alkenes from two halves. One half comes from a haloalkane that is turned into a phosphonium salt that is turned into this anion. The other half comes from a carbonyl. Okay? And the byproduct is triphenylphosphine oxide that is, well, in the old days it used to be thrown away. Now it's recycled because you can reduce it back to the phosphine. So let's look at this in a movie. So first of all, look at so this is the ylid now that we formed from the haloalkane and deprotonation. Just to warn you, these phenyl groups are big. Okay, so there they are. So the ylid is a big beast, okay, with this triphenylphosphine sitting there. And this carbonyl then adds to the, this anion adds to the carbonyl carbon. And here's the carbonyl carbon. So it's standard nucleophilic addition. And now there's a slight twist, this four-membered ring formation. And then cleaving this so-called reverse 2+2 cycle addition, making the corresponding CC double bond. So that, as you can imagine, is obviously a very powerful transformation, because not only do you make a single bond, you make a double bond between two carbon units. So here's some examples. Take this aldehyde on top. With this ylid, bang, you get the CC double bond. Okay? 66%. Remember, this ylid is made from the corresponding haloalkane. Ignore the triphenylphosphine. Think of this as CH bromide, okay? Which, of course, you can make from butane. So imagine taking butane, you brominate it, it goes to the secondary position, you have the bromide, you treat it with triphenylphosphine, that makes the phosphonium salt, you deprotonate, here's your ylid. Okay? Derived from 2-bromobutane. You mix it with this carbonyl, you get the CC double bond, where this half of the double bond was originally derived from a haloalkane. So from now on, when you see a double bond, think of it as retrosynthetically cleaved and makeable by the Wittig reaction of the two components. Retrosynthetically, an absolutely spectacular disconnection, right? Take a double bond and break a molecule into two halves. That gets you down to much, much simpler units. There's also, of course, because of this, the mechanism of this, tremendous selectivity. So when you take this carbonyl with methylene triphenylphosphine and do the Wittig reaction, it will introduce just a CH2 group, so-called methylation. Okay? So if you turn carbonyl into the CH2 group, oxygen turns to CH2, you'll do this by treating this with a Wittig reagent. Notice that this is totally selective, only one isomer. Classically, you would have approached this via some derivative like this by elimination. But when you have something like this, you notice that you can go in all possible directions for the elimination. You can control it somewhat with sterically bulky base. It will give you more of this than that, but you get mixtures. Okay? So that's the problem. This is completely circumvented by using the approach shown up here. So that has given us, I think, 8 new pieces of vocabulary, a little bit of mechanisms, but the mechanisms I'm trying to, what you should do is actually write the mechanisms all next to each other to recognize that they're always the same, just the actors are different. And so rather than memorizing each mechanism, think of the principle and then trust your common sense to pull this off in detail or with a little bit of practice. So we'll leave it at that for today. See you on Thursday. Thanks.